Hello, everyone. I'm Ryan Rad, and I have been in AI for over a decade now, both building products in industry and doing academic research. Recently, I get a lot of questions around AI agents. While there is a lot of hype in this space, I would like to give you my most realistic and honest answer to the top 3 most frequent questions I get all the time. What AI agents are, what they can do right now, and what are some of the main challenges they still face? Let's get into it.
What's the difference between an LLM and an AI agent?
So LLMs are these ultimate next word prediction machines that in an autoregressive way, they will just keep predicting the next word, the word after that, and all the subsequent words. AI agents are actually systems that are built on the top of LLMs. They can interact with the world around them, and they can take actions. Now, to understand what makes a system agentic, the key is to understand the control flow of the system. There are 3 key components here. The action space. Who defines what actions are even possible? Then we have the strategy. Who decides which action to take next and how to navigate through these steps? And third, there is the execution. Who actually produces the output of each step and perform the task? Now, depending on whether an LLM or a human controls those 3 aspects, we can define 6 levels of agency that exist on a spectrum. At the most basic level, we have the code, just traditional programmed instructions where human controls everything. Next is the LLM call, where human design the flow and make strategic decisions, but LLMs are utilized to produce the output by performing a task or executing the step, usually the final step. Then we have chains. These are sequential LLM calls where output fit into inputs. A bit more autonomous, but is still following a fixed path. Moving up, we have routers. Systems that can select different paths based on context. Here, LLM is making some strategic decisions, but they can't look back. They can only move forward in a linear path. Then we have the state machine. Almost all agentic systems that we have seen this year fall under this category. These maintain memory and adjust behavior based on the past interactions. They operate almost independently. And finally, we have the ultimate AI agentic systems. These systems operate with minimal human oversight, not only navigating through these steps and states, but actually creating and defining their own steps as required. Over the last 2 years, there have been a lot of arguments about what qualifies as an AI agent and what doesn't. This spectrum approach is much more practical, as agency exists on a continuum, and different systems fall at different points along that spectrum.
How are AI agents constructed, and what can they actually do?
AI agents are made of 2 main components, LLMs and external tools. Let's see how this works. We start by taking the input, and then we have the LLM components. This is where the LLM thinks about what to do and why. The agent analyzes the situation, considers the options, and take action using those tools or options available. The ability to use tools or tool calling make these agents truly powerful. These can include search engines, knowledge bases, coding environments, various API, or essentially any external capability you want to give your agent access to. After taking action, the agent learns from the outcome, evaluate what happened, and self-correct or use other tools if needed. So this is another thing that makes these agents very powerful, the ability to loop through different tools and the reasoning cycles. This architecture is called REACT, which stands for Reasoning, Acting, and Reflection. This is the industry standard architecture for agents. That's just a single agent. But things get really interesting when we move into multi-agent architectures. There are three main patterns we see in the effective systems here. The first is a collaborative or a network architecture. We have multiple agents working in parallel, each with their own specialization. They share information and coordinate to solve problems collectively, almost like a team of experts with no hierarchy. The second is a hierarchical or a supervisor architecture. In this setup, we have a manager agent that coordinates several specialist agents beneath it. The manager delegates tasks, monitors progress, and synthesizes output from the specialists. And third is a custom domain-specific architecture. The agent structure can be optimized for some very specific workflows. Each of these architectures has its place. Collaborative for innovation and complex problem solving. Hierarchical for stability and control. And custom for specialized domains that requires a unique approach. Let me show you a concrete examples of how multi-agent collaboration work in practice. Here we have two specialized agents working together. We have a researcher agent and we have a programmer agent. The researcher agent has access to search engines and external knowledge bases. It is prompted to find information, analyze data patterns, plan, and generate insight. Then we have the programmer agent that has access to coding environment, any external APIs that might be helpful. And this agent is prompted to write code, debug code, execute code to perform data analysis or create visualization. When these agents collaborate, the workflow might look like this. The researcher discovers a data set online and forms hypotheses and plans how to do the task. And then whenever it's ready, it communicates this finding and requirement to the programmer. The programmer creates visualization code or builds statistical models by interacting with its own tools. Once the results are ready, it goes back to the researcher agent. Both agents can decide to end the session or they can interact with each other for any number of times until they achieve satisfactory outcome. We are seeing these collaborative approaches unlocking new capabilities across many different fields today.
What are the biggest challenges facing AI agent development today?
Let's take one step back and talk about the challenges that an LLM face, and we will take it from there. For LLMs, we have high computational cost, significant latency issues, and hallucinations. These issues become 10x more severe when it comes to agents. The reason is simple math. Where a standard LLM interaction might involve one or two or a few calls, an agent performing complex tasks often requires tens or hundreds or thousands of LLM calls, tool uses, and processing time. Hallucination compounds through reasoning chains. Compute costs scale at each decision step, and latency accumulates as each action might wait for the previous ones to complete, and they depend on each other. When we build agentic systems on top of LLMs, we face additional challenges that can be broken down into two categories. First is the coordination overhead. The first major challenge here is the communication bottlenecks. As agents try to share information, we often see messages getting lost, misinterpreted, or becoming too verbose to be practical. Then there are resource allocation problems. Determining which agent gets computing resources, tool access, or decision-making priority creates significant overhead. Finally, consistency management becomes a major issue. Keeping all agents aligned on the current state, shared knowledge, and overall objectives prove extremely difficult at a scale. The next category is safety and control risks. The first problem here is goal misalignment. This is perhaps the most fundamental safety issue. Agents can interpret instructions differently than intended, leading to behaviors that don't match what users actually want. We have a scope and boundary management as another critical challenge here, setting appropriate guardrails for what agents can and cannot do, ensuring they respect those boundaries requires complex system of constraints. And finally, there are monitoring and intervention challenges. Once agents are running, detecting when they are going off track and successfully interrupting problematic processes is much harder than it appears at first. Thanks for watching. I hope you found this helpful. Please subscribe for more. See you next time.